Hello, this is the paper 2 for the 2017 TMUA. So I've already done paper 1. Paper 2, 75 minutes again, 20 questions again. I mean, the last one took a while. I'm assuming paper 2 is going to be more difficult, so I might do this over 2 videos because I don't really want to be doing an hour plus recording all at once. So we'll see how it goes anyway. Question 1, given that y is that, which one of the following is a correct expression for dy dx? Okay, right, fairly standard opener then. So I'm going to want to expand this out and then split it into 3 terms. And so 1 plus 9x squared minus 6x over 2x to the 3 over 2. And then I can say, okay, well, let's put the half on the outside, x to the minus 3 over 2, and then 9x to the half, and then minus 6x to the minus a half. So y dash, let's leave the half there, minus 3 over 2, x to the minus 5 over 2, plus 9 over 2, x to the minus a half, and then plus 3x to the minus 3 over 2. Okay, they've put the half inside, so let's make that a quarter, and a half. So I've got a plus 9 over 4, so it's not any of those ones. I've got a minus 3/4, so it's not that one. And I've got a plus 3 over 2, so it must be A. There we go. So standardish sort of opener. Question 2, PQRS is a rectangle. Coordinates of P and Q are 0, 6 and 1, 8 respectively. Perpendicular to PQ at Q meets the x-axis at R. So how's this working? So I've got PQ, just trying to get the orientation of this. PQ sort of up here. Then that's going to come down to, oh, okay, right, so we're all in positive territory here. So let's draw this out, or nearly. S will be negative, won't it? So I've got that there at 0, 6. That's P. Q is here at 1, 8. That's Q. Then that side there comes down to R. Let's say that's at x0. I don't know what x is going to be. And then we're going to have S down here. So S is going to have the same change from R as P does from Q. So it'll be x minus 1 minus 2. So I want to get the area of all of this. Well, I've got the length of side PQ easily enough. That's going to be root 5. So how am I going to get the length of the other side? Well, we know it's perpendicular. I've got a gradient of 2 going here. So I have a gradient of minus a half going there. So if I've dropped 8, I'll be going up 16. So x must be 17, not that I specifically need it, but I've got a 16 change and an 8 change. So I'm going to have 8 squared plus 16 squared, square rooted, times root 5. That's what I want as the answer, isn't it? So I've got 256 plus 64. So that's going to be, what, 320? And then a root 5. So what can I pull out of 320 here? Well, obviously we've got 64, so that's going to be 5 lots of that, so an 8. And then, yeah, 8 times 5 is 40, isn't it? Yeah, because I've got a root 5, I've got an 8 root 5 and a root 5, giving me E. No, okay, they've started off tough already on these, I would say. They're quite long-winded and haven't really got going. First term of a geometric progression is 2 root 3. So A is 2 root 3. Fourth term, so that's going to be AR cubed, is 9 over 4. What is the sum to infinity of this geometric progression? Okay, so that means then, so I'm going to get R cubed, if I divide by the 2 root 3, is going to, so 9 over 8 root 3. So that's going to be, well, I could write that as 3 root 3 over 8 then. Okay, but that's R cubed. So I'm going to have to cube root, oh, actually cube rooting that comes out fine, didn't it? Because I'm going to have a root 3 over 2 is R. And then I want sum to infinity is A over 1 minus R. So 2 root 3 over, well, let's say 2 minus root 3, make that a 4. So multiply that by 2 plus root 3, so the bottom will end up being 1. So I've just got that. Is that any of these? Yeah. Doesn't look like any of these. Oh no, it is the bottom one, isn't it? They've just put the root 3 inside the bracket. So I've got 4, yeah, times 2 root 3 plus 3. So G. Okay. Question 4. The following question appeared in an examination. Given that tan x equals root 3, find the possible values of sine 2x. Student gave the following answer. Tan x equals root 3, so x equals 60 degrees. Well, it might do, yeah. And 2x equals 120 degrees, therefore sine 2x is root 3 over 2. Which one of the following statements is correct? So root 3 over 2 is the only possible value, and this is fully supported by the reasoning given in the student's answer. Well, I'm not happy with that because he hasn't really dealt with these options here for tan x. Root 3 over 2 is only possible value. Reasoning should consider other possible values of x for which tan x is root 3. So that's certainly a possibility, depending on whether root 3 over 2 is the only possible value. Then we've got variance on this. Oh, should we be looking at possible values of x for which sine 2x is root 3 over 2? But we want the possible values of sine 2x, so we don't really care about that. We're not looking at x, we're looking at sine 2x, so we don't care about those. And D is the counterpart to B. As to whether root 3 over 2 is the only possible value, right? So how are we going to determine that? Well, tan x cycles every 180 degrees, so does sine 2x. It makes me think we're going to just have the one value, as in if we go up to 180 degrees, we're going to have a full load of sine. We're going to have, this is hard to pick, so that's going up to 180. So we're going to have tan doing this. So we're going to get one intersection for a root 3 on tan, and that's going to be at the same point in every 180 degree cycle. So we're always going to get root 3 over 2. So we don't have to worry about that. So it is going to be B. There's another long question. And they're not all like this. Question 5. Consider the following 3 statements. 10p squared plus 1 and that. Okay, all of these things. Let's see what they actually want. The result 91 equals 7 times 13 can be used to provide a counterexample to which of the above statements? Right, okay, so 10p squared plus 1 and 10p squared minus 1 are both prime when p is an odd prime. Well, they've given us a 10p squared plus 1, haven't they, with a 91. So p is 3, which is an odd prime. And that gives us 91, but 91 is not prime because it's 7 times 13. Right, so that is a contradiction to number 1. So number 1 is fine as being a contradiction or a counterexample, as they've said. Number 2, every prime greater than 5 is of the form 6n plus 1 for some integer n. Is this a counterexample of that? So, well, it is of the form 6n plus 1, but it's not prime. So, I mean, it's not really telling us anything here because they haven't given us a prime number in order to interrogate. So I don't see it being a counterexample to number 2. And then for number 3, no multiple of 7 greater than 7 is prime. Well, of course it isn't, because it's a multiple of 7. So we can't have a counterexample of that because that's just obviously true. So it must be only 1, which is B. Okay, different type of question, that one. Question 6. Right, sequence of that is this. Oh god, right, okay. Up to U 1,000. Right, so these ones are always, we just write them out until we spot a pattern. Seems to be the usual case on this sort of thing. So U1 is going to be integral from 0 to 1 of 4x dx. So that is going to be a 2x squared, so it's going to be equal to 2. U2 is then going to be, well, double that because we're multiplying it by 2, so it will be 4. U3. Oh, we're just doubling each time then. So we're doubling each time, so we're going to have A, 2 to 1,000. Okay, that was a really quick one. Graphs of the two functions are shown here. Oh, graph of two functions are shown here. Y equals a to the x is shown with a solid line. A is a positive real number. Y equals f of x is shown with the dashed line. Okay. Which of the following statements could be true? So, okay, so we're comparing this to, so we've got an a to the x, did they say, and then they've changed it to b to the x or some variant or something. So this is a to the x. So if we were going to do b to the x for the dotted line, well, it's going up higher, so b must be greater than a. So it can't be 1. It can't be 2, but it could be 1. So that's one option. What if we were putting in an extra number there? Well, we'd want it to a higher power. So we'd want 3, but not 4. So 1 or 3. 1 and 3 only, yeah, so E. All right, two quick ones. Back on track. Which one of the following numbers is smallest in value? Okay, so this is, well, that's like just under 3. So let's have that for starters. That is what, an 1/8 and a quarter. So 3/8. So 8 over 3. That's also just under 3. Okay. This is 2 to a little bit. So just over 2. I would say it's probably lower than those ones, but I'm hoping there's going to be a nice one later on. Okay, this thing looks fairly unpleasant. And then we've got for E, well, that's going to be, so sine squared of pi over 4 is a half. So that is 2. Right, so that helps. So it's not that, it's not that, it's not that. So for D, God, I'm really going to have to go through looking at all of this. So I've got a 2 root 2. If I cube all of, oh, I don't know. Well, actually, root 2 minus 1, round about 0.4. And then cube that, and then multiply that by 4. That's a bit annoying, isn't it? Okay, let's write this out. So 2 root 2 minus 3, well, minus 6 actually, wouldn't it? Because I'm going to have a 3 root 2 root 2. And then I'll have a plus 3 root 2 and then a minus 1. And then I need to multiply all of that by 4 and then do 1 over of it. So I've got 5 root 2 minus 7 times 4. Okay, 5 root 2 minus 7. I mean, that's, yeah, it's kind of a fiddly one. I suppose I'm going to have to put this actually. So 5 root 2 plus 7. Let's actually rationalise all of this. And then we've got a 4. So that's going to be 50 minus 49. Okay, right. So it is just coming out as a 1 on the bottom. So, yeah, I mean, that's around about 14 over 4. So, well, it's more than 3. So it's certainly not going to be smallest. So it's going to be E. Right, that felt as though it took me a bit longer than it should have done. 9. Consider the following attempt to prove this theorem. Theorem a cubed plus b cubed equals c cubed has no solutions with a, b, and c positive integers. Attempted proof. Suppose that there are positive integers a, b, and c. Yeah, okay. We have a cubed equals c cubed minus b cubed. I assume we're trying to find what's wrong with this. Is it proof is correct? Well, okay, where's the first mistake? Well, 1 seems fine. Don't think we've got any problems there. Hence a cubed equals all of that. Yeah, I mean, that's just factorising it, so we haven't got a problem there. Follows that a equals c minus b and a squared equals that, since a is less than that. Right, that's a much more involved step. I mean, so we're saying we've got, how are they doing this? All right, so they're splitting up and saying that's a and a squared equals this. So a must be that and a squared must be that. That seems all manner of dubious. because, I mean, there's lots of different ways you can multiply numbers together in order to get the same number. So that really doesn't have to be the case. Yeah. So it's going to be 3, isn't it? Because yeah, these don't have to be the same number. You don't have to say, okay, we've got x times y, and then we've got z times a. So x must be z and y must be a, taking the large one and the small one. We could have two completely different pairs of numbers which multiply to give the same result. So 3 is going to be the first thing they've done wrong. So that's going to be D. At least we didn't have to go all the way down to the bottom. Question 10. F of x is a function defined for all real values of x. Which one of the following is a sufficient condition for the integral from 1 to 3 of f of x dx equal to 0? F of 2 equals 0. Well, that isn't going to be sufficient because we don't know what the rest of it's going to be doing. F of 1 equals f of 3 equals 0. That doesn't really help either. F of minus x is minus f of x for all 0, but that's just reflecting it. No, that doesn't help, does it? Because we're centered here on 2 for x being the middle of the integral. Yeah, I don't see how that helps. D and E, at least we're doing a translation here. If we shift it to the right, then that will certainly help, wouldn't it? If we move it to, no, not 2 to the right, 2 to the left, I mean, because then it will be going from -1 to 1. And then we can show if it's got the rotational symmetry, it'll come out to be 0. So E is looking like a good possibility, is it? Because, no, not E, D, because we want to move to the left, not to the right. E's going to the right, D's going to the left. So if we moved it 2 to the left, f of x plus 2. So we've moved it 2 to the left, we've centered it on the origin, and then we say is equal to minus f of 2 minus x. So yeah, it's got rotational symmetry then. So whatever we're doing there, and then they'll cancel out. So we've got rotational symmetry there once we've shifted it 2 to the left. So yeah, D. Okay. Question 11. Actually, maybe I'll leave it there. I'm halfway through. These do seem to be a bit longer than the questions on the previous paper. So I'll do the first 10 there. I'll do the next 10 in another video, just to break it up a little bit. So yeah, I'll leave it there before I start diving into the back half of the paper. So yeah, back in another video shortly.